Hello everyone. Today I'm going to talk about multi-rate signal processing. It is a very important concept that actually bridges the gap between uh, DSP and advanced DSP. So multi-rate signal processing gives us an opportunity to alter the sampling frequency in discrete representation. So that is a major big advantage associated with the multi-rate. And also multi-rate gives us an opportunity look into wavelet transforms as well, especially from a discrete wavelet transform, and it has a lot of application towards um, uh, image processing related applications. Okay, so for example compression. Um, so, today we are going to talk about the basic components involved in multi-rate signal processing. So let me share the slide. All right. So multi-rate digital signal processing. So there are a lot of advantages of multi-rate signal processing. It reduces the computational complexity. It requires less memory, and most importantly, from a filter design aspect, you can have a lower order filter design. Okay, so there are some basic operation in multi-rate digital signal processing, and those are decimation and interpolation. So we will talk about decimation, interpolation in time domain representation, as well as in frequency domain representation. Before we go into in-depth analysis of that, decimation, what it does is that it decreases the sampling frequency by an integer value. Similarly, interpolation increases the sampling frequency by an integer value. So all these operations are done in discrete time representation given x of n. So one of the basic example of one of the basic advantage of using multi-rate digital signal processing is this. Say for example, the train is passing by, okay, and you want to record the signal, so you use a analog to discrete representation through the process of sampling, so you are able to get x of n. So obviously when you convert from analog to discrete representation, you will have a sampling frequency attached to it. So sampling frequency, so let's assume that you have a sampling frequency, just for the sake of illustration, um, 5k. It's a very hypothetical example, but 5k. Now, with 5k, so 5 kilohertz. Now, what happens is that you do the analysis of the filter design and everything. Later on, you realize that hey, my probably the signal of my train has a higher frequency component than 2500, because that's the uh, Nyquist uh, uh, because because of the sampling theorem, the maximum frequency component a signal can have is 2500 when the sampling frequency is fs. Okay, so later on you realize that hey, I need to alter the sampling frequency. So how do I go about doing that? So shall I record it back with a higher sampling frequency, or shall I do some manipulation in discrete representation such that fs with this 5000 hertz can be decreased or can be increased? In this case, it needs to be increased. So 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 that is the hallmark of a multi-rate signal processing. Is so so in other words, multi-rate digital signal processing allows us to actually alter the sampling frequency. Alter meaning that it can decrease the sampling frequency or increase the sampling frequency in a discrete representation. Right now, decimation and interpolation, they are useful for decreasing and increasing the sampling frequency by an integer value. Key point here is the integer. Now, yeah, now it's reading it properly. So the M-fold decimator, so this is takes an input signal x of n and produces the output sequence yd of n. So decimator m-fold is downward arrow with m here, x of n, yd of n. Yd of n is given as x of m times little n. So this is nothing but x of 3n, 4n. Okay, so n goes from minus infinity to infinity. M, capital M, is an integer. If the sampling frequency is fs of an input signal, then the sampling frequency is reduced by the factor of m. So fs new is fs by m. If you have a sampling period ts, so the ts is increased by a factor of m. So in a lot of books, including P.P. Vaidyanathan's book, which is a classical book on multirate signal processing, Decimator is also called as a downsampler, subsampler, sampling rate compressor, or simply compressor. So we usually use a word for decimator or a downsampling is a commonly used terms. So let me give you a more insight on what exactly is happening through a very simple example. Here, the sampling period is increased by a factor of m. So this is your x of n. So this is given as x of n. So if you look at it, this is the dash line is a continuous time signal. Okay. So that is nothing but your x of t as a function of t. And then these are the discrete representation, which is x of n. Okay. So when you do a sampling of a continuous time signal, you have 0 ts. Okay. Ts is a sampling period. So you're chopping the signal. So 2 ts, 3 ts, 4 ts, so on. So this is a function of t. Now once you get your x of n, then index is there, so you throw out the t. So this is 0, 1, 2, 3, 4, 5, 6, so on, as a function of n. Then you multiply the signal x of n with an s of n. S of n is an integer, is an impulse which is located at every integer multiple of m. In this case, m is 3. So that's why you have a value 1 at 0, 3, 6, 9, so on. Then you multiply these two signals. Once you multiply these two signal, you get xs of n. So in this case, once you multiplied, so 1 and 2 would be the sample value at 1 on 2 will be 0. So this value will be there, this value will be there, this value and this value. So this is 0, 3 ts, 6 ts, 9 ts. Then what you do is that since then you drop down these 0 values 1, 2, sample 5, 4 and 5, 7 and 8. Once you drop down, then you get a y of t, which is the same thing as what is shown after dropping out these 0 value samples. So this is called as ts prime, which is nothing but 3 times ts. So the sampling period is increased by a factor of 3, thereby the sampling frequency is reduced by a factor of t. So another example is this is x of n given, and then this is yd of n. So clearly when you see it, m is equal to 2 because you are keeping every even sample. So 0 will remain the 0, 2 will now be seen at 1, and minus 2 value would be seen at minus 1. That we know through the time scaling property. Now, second one is an L-fold expander. It takes an input signal x of n and produces an output sequence ye of n. Okay, so ye of n is given by x of n by l if l is an integer multiple of, sorry, ye of n, x of n by l if n is an integer multiple of l and 0 otherwise. So in terms of the multirate structure, you have x of n. Now you have an upward arrow L, ye of n. If the sampling frequency is fs, now the new sampling frequency will be increased by a factor of L. So if the sampling period is Ts, the sampling period is reduced by a factor of L. Expander is also called as an upsampling sampling rate expander interpolator. So we use upsampling interpolator as a commonly used word for expander. Not sure how much you can see this. uh, so again, it's just a sake of illustration. So you have x of n as a function of n. The dashed line is a continuous time signal. You have this ts, so you have a sampling period ts. Okay, so 0 ts, 2 ts, 3 ts value. Now l is equal to 3. So what you do is that between two adjacent samples you need to put L minus 1 0. So 0 and 1 you need to put two zeros. So 0, so this will become 1 and 2, and this value would be seen at 3. And so this value would be seen at 6, 5, 4 and 5 would be 0. This value would be seen at 9, 7 and 8 would be 0. So in this case, what you have observed, so in this case what you have observed here is 3 ts prime is ts. So that means that ts prime is ts by 3. So that means that here the sampling period is reduced by a factor of 3, whereby the sampling frequency is increased by a factor of 3. Another example for an expander, so this is x of n is given. You see this x of n 0 to uh, 0 to n. So this is signal just for the sake of illustration. So L is equal to 2, meaning that ye of n, between the two adjacent samples you put 1 0, between these two samples you put 1 0, and so on and so forth. Important point: it is difficult to recover the original signal x of n from yd due to the loss of information, because you are extracting some samples from Decimator. Okay, so that means that you are going to lose the information. However, we can recover the original signal x of n from ye of n, because of the fact that if you put, say for example, l if you put first the expander, so that with a factor of L or a factor of 3. So that means that you put two zeros between the adjacent samples, and then if you decimate by a factor of 3, then those two zeros which was added in due to the expander can be removed. Okay, so that can happen, but once you do a decimator, you are going to lose the information because it's a time scaling property. Okay, so same thing, from an expander and decimator you can do it. From a decimator to expander you cannot do it, because obviously decimator results in loss of information. Frequency domain characterization. So that till this point we spoke about time domain representation. This is a frequency domain characterization of an expander. Ye of z, summation of n goes from minus infinity to infinity, ye of n z to the power of minus n. So ye of n is given as x of n by L if n is an integer multiple of L, 0 otherwise. Excuse me. So if you compute the z transform, ye of z is nothing but x of z to the power of L. Now one important point you need to remember is, so in the frequency domain, z is equal to e to the power of j omega. E to the power of j omega would be x of e to the power of j omega, evaluating around the unit circle. We know that x of e to the power of j omega is periodic with a period of 2 pi. Then x of e to the power of j omega L would be periodic with a period of 2 pi by L now. Okay, so ye to the power of j omega is an L-fold compressed version of x of e to the power of j omega L. So what I mean here is, so this is schematic. This is the one of the example from the book from PP Vaidyanathan's book. So this is x of e to the power of j omega. So let's see, it's between 0 to 2 pi. Obviously it's periodic with a period of 2 pi as a function of omega. Now now the expander is applied with the factor of L. So this entire expression, if you see here, 0 to 2 pi, sorry, the entire sketch between 0 to 2 pi will be compressed to 0 to 2 pi by L. So that means that 1 2 3. Okay, this is one version. Then over the interval of 0 to 2 pi, you will have or the original and also 1 2 3. So this is 1, this is 2, this is 3, this is 4. So you have one original and 4 replica of the original because it gets compressed. So the original is between 0 to 2 pi by L. Okay, from 2 pi by L to 2 pi, you will end up, because L is equal to 5, so you will end up with 4 images. We call this as an images. This is the um, consequence of increasing the sampling frequency by a factor of L. In this case, you will end up with L minus 1 images in the frequency spectrum. And those frequency spectrum, you have to filter out such that this should not be here. These images should be suppressed. So we'll talk about the filters aspect later on. Frequency domain characterization for a decimator. So yd of z is equal to summation of n goes from minus infinity to infinity, yd of n, z to the power of minus n. Then later on, this is the, I'm not going to math associated with it. This is the derivation. This is the final z transform expression. Yd of z is equal to 1 over m, summation of k goes from 0 to m minus 1, capital X of z to the power of 1 over m wkm, where wm is equal to e to the power of minus j 2 pi by m. So if I want to put it in the frequency domain representation, z is equal to e to the power of j omega. If I put, I'm going to get this. Now, agreed that this is the expression, which is a little complicated than the expander expression, but let's try to understand intuitively what is happening. If you understand intuitively, then you don't need to really memorize what is actually in this frequency domain representation. This is the one example, decimator example, m is equal to 3. So x of e to the power of j omega is given. So you can clearly see that it is periodic with a period of 2 pi. So, and it's a band limited signal with plus or minus pi by 3 in the triangular shape, and it's periodic with a period of 2 pi. Now, this frequency or this input signal x of n is passed through a decimator, and I want to get the frequency response of the output coming from the decimator. So the first thing what you do here is you get x of e to the power of j omega by 3. That means that you multiply the x-axis by 3. By doing that, this becomes minus pi to pi. This will become 6 pi, and this will be minus 6 pi. That's the first step. Second step, what you do is that you shift this panel in the B with a factor of 2 pi. So x of e to the power of j omega minus 2 pi by 3, 0, this triangle would be seen as 2 pi, this triangle would be seen at 8 pi, this will be seen at minus 4. Then, because since m is equal to 3, so k goes from 0 to m minus 1. So it means that, so k is equal to 0 to 2. So k is equal to 0 would be this, k is equal to 1 would be this, and k is equal to 2. Again, you shift this expression by 2 pi. So this will become minus 4 pi. So this is minus 4 pi would be seen at minus 2 pi, 2 pi would be seen at 4 pi, 8 pi would be seen at 10 pi, which is outside the box. Now, what you do is that you add across all these panels, B, C, and D. Once you add it, then obviously what happens is this is minus pi to pi. This gets like this. Okay, and this is 1 by 3 is there, 1 by m. So I put 3 times yd of e to the power of j omega so that I can make this 1. If you want to remove this, you can make this as 1/3. That is not an issue at all. So what is happening is that the adjacent frequency spectrum is not overlapping. So aliasing does not happen. So to avoid aliasing, mod of omega should be less than or equal to pi by m. Correct? Less than or equal to, in this case, m is equal to 3. So mod of omega should be less than or equal to pi by 3, which is correct. Now, I'll take another example where m is equal to 3. Okay. But mod of omega is greater than pi by 3. So in this case, this is pi by 2. So I'm certain to know that this is going to happen. Aliasing will happen. So first thing what you do is that you multiply this by a factor of 3. So this becomes minus 3 pi by 2. This becomes 3 pi by 2. Okay. And then similarly, you can get the other values as well. Now you shift this with a factor of 2 pi. So this is 2 pi, meaning that this is the plot point here. So this is the triangle which is coming up. Again, you shift by a factor of another 2 pi, which is going to be here. Now what you do is that once you add it, what is happening is that between the interval minus pi by 2 to pi by 2, you are going to get the triangular shape. Afterwards, pi by 2 to 3 pi by 2, the slope is going down, slope is coming up. So it has the same slope. So it will be when you add it, it's going to be a straight line. You will see a straight line. And then from 3 pi by 2 onwards, again you get this small triangle, and then this state, and this is the pattern. So this is aliased. So adjacent frequency spectrum overlaps. So this is a case of an aliasing. So now there are two things which we need to understand. When you are decreasing the sampling frequency, you need to be extra careful about whether you are going into an alias domain. Okay, we try to minimize, or we try to avoid the aliasing thing. Okay, that's one. With the for the expander, what happens is that you can increase the sampling frequency, but it comes with a catch that you end up with L minus 1 images, which you need to do. This brings up to an important concept of a decimation filter. What is a decimation filter? Okay, so decimation filter, because obviously there is a possibility of aliasing, we put a decimator filter is before the decimator, and the decimator filter is generally a low pass digital filter. So the filter ensures that the signal being decimated is band limited to avoid or minimize aliasing, meaning that mod of omega should be less than or equal to pi by m. So what we do is that before we pass through a decimator, we apply a decimation filter such that we can minimize or avoid the effect of aliasing. Okay, obviously the exact band edges of the filter depends upon how much aliasing can be permitted. So the frequency characteristic of this filter, obviously, this is the ideal representation I am showing, but obviously, practically speaking, you will have a transition band, and then it will be a monotonically decreasing function. So mod of omega less than or equal to pi by m, the value is 1, and it is 0 otherwise. So we make sure that the signal is band limited to avoid aliasing. Okay. But since even though you apply a filter, decimation filter, but the actual frequency component in your x of n is already lost. So that's why what we say is that to minimize the aliasing effect. Okay. So the interpolation filter, what happens with the interpolation? The interpolation filter comes after the expander, because the interpolation introduces the images. So we want to remove those images. So again, this filter is a low pass filter, and its main purpose is to suppress the images that are created by the expander. So again, the frequency response of the interpolator h of e to the power of j omega should be L, mod of omega less than or equal to pi by L, or 0 otherwise. So now two important points again, just to summarize. You apply a decimator filter before the decimator to make sure that the to make sure that the aliasing is avoided, or aliasing is avoided or minimized as much as possible, and then you apply a interpolator filter after the expander to make sure that uh, the images which are introduced due to the expander are suppressed. Okay, so now this is another example where what happens to the effect of interpolation on time domain representation. So you have your x of n here, you have your x of n, this is your x of n. Now you put l is equal to 2, so between the two adjacent samples you are putting one zeros, which you can see it here. After the interpolator, then you are going to put a filter. So filter nothing but this is a filter response h of n, you do the convolution. So obviously you get this some uh, filtered value which is shown in x of n. But the effect, important point is, the effect is that the zero valued sample that has been introduced by the expander are filled due to the filtering operation. Okay, so I hope so far it is clear to you of what I'm talking about. As I said before, I'm just touching a little bit on the important concept of multi-rate digital signal processing. So far we have discussed about decimation, interpolation, both in time and frequency domain, and what is a need to have a decimation filter, what is a need to have a interpolation filter. Now practically, uh, you want to alter the sampling frequency of your signal by some rational value. That's more a practical application. So that brings up to a very important concept of a fractional sampling rate alteration, which I'm going to talk about that here. Okay, so technique discussed so far will either increase or decrease the sampling frequency of the signal by an integer value. So L and M are an integer. But for a real-time signal, it may be necessary to change the sampling frequency by a rational function, for example, L by M. So this is a very important example again from P.P. Vaidyanathan's book. So this is given as this is the frequency spectrum. So x of e to the power of j omega is band limited with plus or minus 2 pi by 3, and then from there I need to get y of e to the power of j omega, which is plus or minus pi by 3. What happens if I decimate by a factor of 2? If I decimate by a factor of 2, then this plus this would be seen at minus 4 by 3 pi and plus 4 pi, sorry, minus 4 pi by 3 and 4 pi by 3, which is beyond um, the range which we are interested in. So the point here is we need to decimate by a factor of 1.5. So 3 by 2. So 3 by 2, if I multiply, then this becomes plus or minus pi. So from plus or minus 2 pi by 3, it goes to plus or minus pi if I decimate by a factor of 1.5. So but 1.5 I cannot decimate so far. So that's why what we will do is that we will adopt the combination of these multi-rate structures. So one procedure could be, which is very tedious, is to convert the discrete sequence into a continuous signal and then resample at a different sampling rate as per your requirement. This may or may not be feasible. Then alternative option is to do samplings fractional sampling rate alteration directly in a digital domain. So fractional sampling rate alteration includes the combination of a decimation and interpolation. So now same question, should we first decimate or interpolate is the first thing that comes our mind. So what we need to do here is, what happens if we decimate? We have already discussed. Okay. What happens if I interpolate? Interpolate meaning that it will be divided. So what happens if I interpolate by a factor of L? L is equal to 2. So if I do that, then this becomes 2 pi by 3 times 2. So this will become plus or minus pi by 3. And then afterwards, I can decimate by a factor of 3. The example which we have seen. So it becomes plus or minus pi. So that's what we are going to do. So first thing is that we are going to interpolate by a factor of L is equal to 2. So this solid line, this plus or minus 2 pi by 3 would be seen at plus or minus pi by 3. Okay. And then another image will pop up over the interval. Okay. Over the interval of 2 pi. So this is obviously the period now is being reduced. Okay. From period is also reduced. Okay. Because 2 pi, so 2 pi by L. Okay. So you are going to get this, and then this is the another image which is coming up. Okay, compressed version. Okay, so now I need to remove this. So for that I can apply a low pass filter in such a way that only this particular frequency this particular triangle is preserved, and this is removed. So I can have an ideal filter, or I can have a more practical filter where it is monotonically decreasing, just to make sure that uh, between plus or minus pi by 3 the information should be intact. So I can have a filter which can satisfy that. Then then I get plus or minus pi by 3. Then I can decimate by a factor of 3. Okay. So what we have done so far here is we are interpolating by a factor of L. Then we are passing through a filter. Okay. And then finally I'm going to get this after the filtered one. And then we decimate by a factor of 3 to get plus or minus pi for y of e to the power of j omega. So in terms of the block diagram, what we are doing here is general form is whenever you apply a decimator, whenever you applied an interpolator, you need to have an interpolation filter. And then before applying an decimator, you need to have a decimator filter. I can combine these two things, and then I can put it in the form of h of z. So up L, which is an interpolator, passing through a filter h of z, down M, which is a decimator. So if the sampling frequency is Fs, then after the interpolator, it is L times Fs. Then after the decimator, it is L by M times Fs. So what is the frequency response of the filter h of z? H of e to the power of j omega. The gain should be L. Mod of omega should be less than or equal to minimum of pi by L, comma pi by M, and 0 otherwise, because you need to take care of both the interpolator and the decimator. So that's why we take a minimum of pi by L, comma pi by M. Hope it is clear, the concept of fractional sampling rate alteration. Now I'm going to talk about interconnection of the building blocks. So so can we so in order to come up with a computationally efficient multi-rate system, we may need to swap the position of a filter or a multiplier or an adder with a downsampler or an upsampler. So this is so given these three, so we need to see that which one is more efficient. So you are downsampling by a factor of m and then multiplying. This is the same thing as you are multiplying first and the downsampling. So there is no point in multiplying all the values of x of n by some value and then again downsample. Okay, so this is more efficient way. You want to add both the signals and then downsample, or you can downsample the individual signal by the same downsampling factor, which is m, and add it. So in this case, this is the second one is more efficient. The last one is modulation, so multiplying. So x of n is multiplied by d of n. So you take a multiplication of all the samples of n and then decimate by a factor of m. It is the same thing as you take an x of n decimated separately by a factor of m, d of n decimated separately by a factor of n, and then multiply. So this is more efficient, this is more efficient, and this is more efficient. So the same property would hold good if you replace the decimator by an interpolator. This is another important concept of a decimator interpolation cascade, because we talk about that quite often when it comes to simplifying the multirate structure. Okay, so this is given x of n down m up l to get y1 of n, x of n up l down m to get y2 of n. Okay, so let me first derive the expression for y1 of z and y2 of z. So first thing is that I'm writing down the expression for what happens to the interpolator and what happens to the decimator in z transform. This is the expression given. So y1 of z is this is the decimator, so it takes this formula, and wherever it sees z, it replaced by z to the power of l. So z to the power of L by m, WKM. In this case, for the second one, you have interpolator first. So x of z to the power of L, and z is replaced by this. So that means that what happens here is that L comes here, L by m, as well as WKLM. And then the rest of the things are the same. So on what basis or on what condition of m and L, the output y1 and y2 would be the same. So we call this as an decimator interpolator cascade. So in order to see that, this just boils down to a simple expression to identify for which cases of k, which cases of m and l, wkm is equal to wklm. Okay, k goes from 0, 1 to m minus 1. This condition will be equal only when L and M are relatively co-prime numbers. So that means that there is no common factor between the two. So for example, 2 and 3, 4 and 5. Okay. So there should not be any common factor between the two. Okay. Thus, the output of the decimator interpolator cascade y1 of z and y2 of z are are identical if and only if L and M are relatively a prime number. So, for example, 7 and 5, okay, 2 and 3, 4 and 5. So, if that happens, then in those cases, you can switch the order. So, you can switch up M, down L to down M, up L to up L, down M. Okay. Noble identity is a very important concept associated with multi-rate signal processing for simplification of multi-rate blocks. Okay, I'm just going through it in a brief way. Derivation can be done later on also. This identity describes that it is possible to reverse the order of the decimation and interpolation with filtering aspect. So what this is telling is you have x of n is there, upward L, h of z to the power of L, y of n. So that means that you put in L minus 1 zeros and then passing through a filtering operation. That is much better than doing the filtering operation first with h of z instead of h of z to the power of L, and then do the upsampling by a factor of L. So mathematically, y of z would be the same, x of z to the power of L, h of z to the power of L. It's not going to change. Then this is a second noble identity which says that when you pass through an x of n, you pass through a filter h of z to the power of m, and then you do everything. Then you do the downsampling. Again, this is not an efficient way. So what you can do is that you can downsample the signal first by a factor of m, and then you can apply h of z to get y of n. Again, the expression of y of z would be the same. So this we call it as an identity 2. So this is the identity 1. I think so. X of n up L, h of z to the power of L is the same thing as h of z up L. Okay, and then um, that is the identity one. Identity two is x of n is passed through a filter h of z to the power of m down m is equivalent to down m h of z to get your output. So this is the final output for this scenario. This is the final output for this scenario. This is for the decimator z transform representation. Okay. So now, based on the identity 1 and identity 2, we try to simplify the multi-rate structure. So this is a very simple example. X of n is given up to z to the power of minus 2 down 2. So this is nothing but this is a interpolator. This is a decimator. Now what I can do here is I can use I can use the identity too. By doing this, this can move here. But since I am moving this, z to the power of minus 2 would be seen at z to the power of minus 1, because z to the power of minus 2 would be divided by 2. Z to the power of minus 2 divided by 2. So that is z to the power of minus 1. Up L, down 2 is the same. So you have z to the power of minus 1. This entire multi-rate structure, which has multi-rate interpolator, decimator, and then the filter, when once you use the noble identity, it can be reduced to z to the power of minus 1 as the transfer function of this particular system. So your y of n is nothing but x of n minus 1. It is delayed by one particular sample. Okay, I hope this is clear to you of what I have spoken. Now what I'm going to do is I'm going to go through some more examples just to make sure that you are you are able to understand the concept of fractional sampling rate, alteration, and the noble identity. Okay, so this is one example. We wish to convert the data sampled at a sampling rate of 44.1 kilohertz, for example, in a compact disc, to a sampling frequency of 48 kilohertz as a digital audio tape to facilitate the data transfer from a CD to a digital audio tape. Design a suitable multi-rate structure. So we know that my Fs new is nothing but L by M Fs old. Okay, so L by M is nothing but Fs new divided by Fs old. Fs new is 48 kilohertz and Fs old is nothing but 44.1. So if you simplify it, I get 160 divided by 147. Make sure that you simplify, you put this expression in a simplified form. Then your multi-rate block would be x of n up L. Up L will be 160. You have a filter h of z. Down m in this case is going to be 147. So your frequency response of the filter h of e to the power of j omega, the gain will be 160, and then you take so this should be magnitude. Okay, magnitude. So omega c should be less than or equal to minimum of pi divided by 160 comma pi divided by 147. So the minimum will be pi divided by 160 and 0 elsewhere. So the gain of the filter in this case is 160. Okay, so this is how you can design a fractional sampling rate alteration method to make sure that you can facilitate the data transfer from a old sampling frequency to a new sampling frequency. Now, use noble identity to simplify the following multi-rate structure. Determine y of n in terms of x of n. So this is given to me x. So x of n, z to the power of minus 4, down 2, up 3, down 2. First thing you see when you see 2 and 3. So that means that what you can do, you can move it together, meaning that you can use a decimator interpolator cascade. So down 2, up 3, I can move to up 3, down 2, down 2. So when you have a down 2, So that is going to be down 2 into 2, not 2 plus 2. Okay, 2 into 2. So that is down 4, up 3, z to the power of minus 4. Now I need to apply a novel identity. I have not applied the novel identity. So what I'm going to do here is I'm going to do the novel identity one, move this interpolator here. So if I move this interpolator here, then what happens? So if you, my interpolator is 3 here, z to the power of h of z. Now, if I have to move this, that means that I have to multiply z to the power of minus 4 into 3 here. So this becomes z to the power of minus 12, up 3, z to the power of minus 12, down 4. Now what is my, so this is for the sake of illustration, both the identity has been applied. You can use the other approach as well. So you can do, because 3 and 4 again it's a cascade of a decimator interpolator. You can alter it and then you can do that simplification as well. So in that case you may have to use the novel identity too. Nevertheless the answer is going to be the same. So I'll just slightly zoom out just to make sure that you can see what I'm talking about. So this is x1 of n, y1 of n, y2 of, sorry, x1 of n, v1 of n, v2 of n, y of n. So v1 of n is nothing but x of n by 3. V2 is nothing but, this is a delayed, V2 of n is nothing but V1 of n convolved with delta of n minus 12. So this is V1 of n minus 12. So x of, wherever you see x, wherever you see n, replaced by n minus 12. So x of n minus 12 divided by 3. And then later on you have a down 4. Down 4 meaning that y of down 4 meaning that y of n is equal to v2 of 4n. So wherever you see n here, replaced by 4n. So x of 4n minus 12 divided by 3. This is going to be the uh, answer for this. Okay, then the last question which I wanted to discuss is use novel identity to simplify the following multi-rate structure. So this is the multi-rate structure given to you. This looks very big, but if you take it a little bit closely, three things you need to see: noble identity 1, noble identity 2, and if you see whether you can apply interpolator, decimator, cascade, and then you want to see whether it is up L, down L, then it will be nullify the effect. These are the four things which you need to see. So this is the structure given. What I am going to do here is, first thing is that I'm going to apply the novel identity 1. I move this and put it here. So this will become 1 plus z to the power of minus 4. So this now this will be brought up together. So you have down 4. Okay, because down 2, this is 2 into 2, this becomes down 4. Now what you do next is, this you can simplify. Okay, but what I want to do is that I don't want to simplify this. I want to apply a noble identity 1. To move this, I can move this with a, I can move this, but z to the power of minus 4 would become z to the power of minus 1, which is this. Then down up 4, this is up 4, down 4. So this is nothing but it's going to be the same. Okay, so this is the same, so state. So then I take a product of these three terms and finally I get this expression. So your h of z is nothing but 1 plus z inverse minus z to the power of minus 2 minus z to the power of minus 3. Okay, so 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 what in this lecture what I have done is I have talked to you briefly about multi-rate signal processing, what is its significance associated with it, time domain representation of an interpolator, decimator, and again its respective frequency domain representation, decimation filter, interpolation filter, what are the needs for that. Okay, those are the two important things which we have discussed. We also just discussed about the fractional sampling rate alteration, what is the need for that. Okay, then we discussed about interpolator, decimator, cascade. So you have to make sure that L and M should have a should not have any common factor between the two. Okay, relatively co-prime. That is the one. Then we discuss about the noble identity 1 and 2. So the noble identity 1 and 2 says that it's possible to make sure that you can alter the positioning of your interpolator and with the filter, and similarly with the decimator and the filter, to make sure that it is more efficient. And the idea behind here is that given a complicator on a multiple stages of a multi-rate block, with the help of noble identity decimator interpolator cascade, you can actually simplify it to a shorter version. Okay, so this is what I wanted to discuss today in terms of multi-rate signal processing. Okay, okay, thank you very much.